Okay, let's start. Today I'm going to finish the overlay of two subdivisions. We talked about it very quickly, how we find the inner components and outer component records of a face and the incident face component of an edge using this constructing a graph of boundary cycles. We were talking about it, but we had to cut it short quickly last week. So I'm going to talk about it and finish that. And we are going to start a new problem. We are going to a new chapter, which is guarding an art gallery and polygon triangulations. Again, we are going to see a plane sweep algorithm to triangulate a polygon. You are going to see. So plane sweep is everywhere. It's used it's used in many algorithms in computational geometry. You are going to see this. And your homework is due today. You can either submit it now or you can do it in the break. And for the homework, maybe for certain cases, I mean, I may not have given you all the assumptions so that this traversal, clockwise traversal is possible in every case. There may be certain cases when the connectivity of the faces surrounding the vertex may not be well defined. For example, if that vertex is incident to the unbounded face, that may be a problem, for example, if it's incident to the unbounded face, because I mean the unbounded face is going to be everywhere surrounding the vertex. That may be a problem in traversal, but so you may have to, either you can give this as a counter example. I mean, since I didn't give you as an assumption, you can say that for these cases, the clockwise traversal is not possible. Or maybe what you can do is assuming the vertex is incident to bounded faces. If all the incident faces of this vertex are all bounded, then it may be possible to do the clockwise traversal, and you may prove your claim based on this assumption. So both are possible. So the idea was to know more about doubly connected edge list, and I hope it worked out good in terms of, for example, the next edge of an edge you see can be sometimes, if you don't know what the edge is doing, if you don't make use of the incident face record of an edge, actually, the next edge of an edge, for example, it can be many things. So if this is my half edge and there are two edges going like this, which one is the next edge of this edge? Okay, so, and the idea is that the next edge helps us to walk along the boundary of a face. Okay, so the current edge, if this is my edge, the current edge and the next edge of this edge have to bound the same face. Okay, so next edge allows us to walk along the boundary of a particular specific face. So in that case, if this is going to be the next edge of this edge, because what we do is every half edge uniquely bounds the face, the incident face of every half edge lies to its left. Okay, so this edge bounds, if there's a face here, this edge bounds this face. Okay, so we need the next edge that we are looking for also should bound the same edge. So the next edges and previous edge records, they share the same edge. So working on this problem, probably you notice things like that. So I hope it helped you to understand the doubly connected edge list data structure better. Now, let's. Do you have any questions about homework? Okay, so let's come back to our problem. After we have found the vertices and half edge records correctly using the plane sweep algorithm of the overlay of two subdivision, the next step was to find the inner component and our outer component records of each face, and also to set the incident face record of each edge. And we do it after we have all the half edges. By traversing all these half edge records, we can first identify the boundary cycles. So that's the first step. After you know that all the half edge records you have are correct, and the vertices, all the vertex and half edge records are correct, the next step is to find the boundary cycles. How do you find the boundary cycle? Because the next edge record you think is also done correctly during the first plane sweep. By following the next edge records of these, each edge, in the first algorithm you have done this, you found a cycle. Okay, you hope by going over all next edge records, you are going to come to the same edge. So you assume that there is all edge belongs to some cycle. All edges, all half edges belong to some cycle. And after you detect this cycle, I described an easy way to find out whether that cycle is counterclockwise or clockwise. So we find the leftmost vertex of that cycle, and if the inner angle of that leftmost vertex is less than pi, it means it's counterclockwise. Let's see. So it's we look at the halfmost vertex. Okay. So this, by looking at just these two, you don't know whether this is a clockwise traversal or a counterclockwise traversal. Somebody has to also give you what is the inner part of this boundary. If this part is the inner part of the boundary, it means it's a clockwise traversal. If this is the inner part of the boundary, it means it's a sorry, it was vice versa. If this is the inside, it's counterclockwise. If this is inside, it's clockwise. Okay, so this is counterclockwise. If this is the inner angle. If this part was the inner angle, which is greater than pi, what we are doing is we have this traversal, which is clockwise. So after detecting the boundary cycles, with the simple rule, we can label each of these cycles as either an inner boundary or an outer boundary. The half edge cycles, which as clockwise, are going to be the inner boundary of some face. They are going to be the holes. Okay, so if we have a clockwise traversal, so imagine we have faces and we have half edges, and they are like this. Okay, since the rule, the half edge, the incident phase of the half edge always lies to its left. What does it tell you? Its face is here. Okay, so here is its face, because the left hand side of all these edges are, the left hand side of this one is here, the left hand side of this one is this one is this one is this. So it gives you that if we have a clockwise traversal like this, its face lies outside, so it bounds a face at the outside, meaning that it becomes a hole of that face. Okay, if it's a clockwise traversal, and if it's a counterclockwise traversal, it's an outer boundary of its incident face. So what we do is we construct a graph. After finding for each boundary cycle, we create a node in this graph. Each boundary cycle is going to be represented by a node, and we are going to have an additional node for the imaginary unbounded face. So if we have found, for example, n boundary cycles during traversing these edges, if we have found n boundary cycles, you are going to create a graph with n minus 1 nodes. Okay, a graph with n minus 1 nodes. We have a node for every boundary cycle. Some of these boundary cycles, for example, imagine this one. Okay, this one also has half edges, right? Its half edges also may define another cycle like this. So for the same part here, we are going to have two nodes. One for the black outer boundary of this face, and one for the inner. So we are going to create two nodes because these are two separate boundary cycles. One of them is counterclockwise, the other is clockwise boundary cycle. So these two are two different boundary cycles. So we are going to create two different nodes for them and label one of them. The outer boundaries are going to be represented. The book represents outer boundary with two circles like this. So we are going to have at the end a graph with as many nodes as the number of boundary cycles plus 1. So there is one node for the unbounded outer boundary. There is one. So we have an unbounded face. The imaginary boundary of the unbounded face is also an outer boundary. So we have a node for that. So we identify the nodes in our graph. So how are we? The next step is how are we going to find the edges in this graph? Because we are going to use this graph to find boundary cycles that are incident to the same face. What does this mean? So each sentence actually in this the computational geometry, sometimes you may need time to grasp all the information. That's the bad thing. The book may be a short book, but reading it takes really a long time. I'm understanding every concept in detail. Finding all the boundary cycles that are incident to the same face. For example, if there are 5 boundary cycles incident to the same face, meaning that 5 boundary cycles bounding the same face, what does this mean? 4 of them are holes, 1 of them is the outer boundary. Okay, this is what it means. So it's not immediately apparent when I say five boundary cycles bounding the same face, but if I tell you the other way, I'm saying if this face has 4 holes and 1 outer boundary, this is exactly the same thing. Okay, so if a face has 5 boundary cycles, if 5 boundary cycles are incident to the same face, it means that 4 of them are holes of this face, and 1 of them is the outer boundary. Now, yes? Yes, sure. So imagine there is a face like this with holes. So this is my face, and there are holes in it. Okay? So I'm going to have boundary cycles which are clockwise. For these boundary cycles, I'm going to have a clockwise. I'm always mixing these clockwise and counterclockwise. So the inner holes are going to be clockwise. Okay. So I'm going to have boundary cycles which are clockwise, and I'm going to have also boundary cycles. The half edges of these are going to be counterclockwise, but they are going to be bounding this face in the middle. Okay, this is the half edges of this clockwise boundary cycle. The other part is going to be the outer boundary of this face in the middle. But now we are interested in this face. Okay, look at this face F. Okay, in order to identify this face F, what bounds this face F? This inside part. This is my face F. Okay. So all the red region is my face F. How many boundary cycles do I need to represent F? I need 4 boundary cycles. One is bounding the face F on the outside, and these 3 are bounding the face on the inside. They are holes. This face does not go through these holes. These holes bound the face. Okay, the holes are not included in the face. They are excluded in the whole. Only the red region is my face. So, therefore, these clockwise boundary cycles in the so if you look at these clockwise boundary cycles, and if you look to the left of these cycles, you are going to see the red region. The left part of these cycles is this face. And the right part, so if imagine yourself walking on the boundary. If you're walking on the boundary, the face, the red part is always going to lie to your left, okay? If you're in this clockwise traversal. And the outer boundary is going to be counterclockwise, this way. And again, if you imagine walking yourself on the outer boundary, again, the red region is going to be always to your left, okay? So these 4 boundaries, the 3 inner boundary and 1 outer boundary, are the boundary cycles that are incident to the same face F. So I find 4 boundary cycles and they are all incident to the same face F. My goal is to find these. First, what I did was in the first step, I just found the boundary cycles and I created nodes for them. Now, the next step is how can I find that which holes, a subset of these nodes, like 4 of them, may be bounding the same face. How am I going to find this? We are going to do it by defining edges on this graph. And we are going to define edges in such a way that at the end, each connected component of this graph is going to correspond to a particular face. Okay, so this is going to be the main idea. We are going to create edges, and when we do that, we are going to see that each of them is going to be linked. These are going to be linked to each other, and they are going to also be linked to this outer boundary, and this connected component is going to give us these connected components is going to give us the face information. Okay, so yes. So this is not the same F, sorry. Yeah. This is, for example, if this is F1, this is F2. This is a different face. No. This boundary is not related with F2. It's twins, actually. It's twin boundary, which is, let me use a different color, is what is bounding F2. So the counterclockwise version, the reverse version of this boundary is the boundary of F2. And F2 has a single boundary. It doesn't have any holes. It just has a single boundary, which is this blue boundary. Okay, that's a different face. Now, the idea is this. We define an edge like the following. Here is the exact description for that. We put an edge between a whole boundary cycle. So if we are going to put an edge, one of them have to be a clockwise boundary cycle. It has to be a hole. Why is that? Because a face cannot have 2 outer boundaries. We don't want to put an edge between 2 outer boundaries. I mean, if at the end our goal is going to be have connected components indicate a single face, the invariant in this at the end of this algorithm is that no 2 outer boundaries should share an edge. I mean, they shouldn't be connected. They shouldn't be in the same connected component. So if one of the boundaries is a hole, if one of the nodes indicates an inner boundary, a hole, we put an edge to the boundary cycle immediately to the left of it, but not this time the left definition is global left definition. It's not considering the local half edge left definition. So what we do is, for example, we connect, let me use the example in the book actually, which demonstrates it better. Let me draw the whole thing and the whole graph. It's going to become more clear. Okay, so here is my subdivision. It has how many faces? Let's see. Yeah, it has 7 cycles in it. So we have one big cycle on the outside, which is the, Okay, so let me use longer. So we have something like this on the outside. So this is clockwise, as you can see, and this clockwise cycle is going to be the whole of our unbounded face. Okay, we have an unbounded face here, and this is the whole of that unbounded face. And the clockwise version of this, I'm going to use different colors for inner and outer boundaries. So the counterclockwise version, the half edges, okay, is going to be the outer boundary of this face. This face, it's the outer boundary of this face, and I have an unbounded face here, in which the black cycle is the inner one of the. It's an inner component. Now let's have two other things. A counterclockwise. And a clockwise one. Also, these are the half edges. And I'm going to have two of the same thing. Okay. I have two more faces in which these boundary cycles, this one, and okay, its half edge is also going to be like this. Okay, so I have one cycle going like this, counterclockwise, another cycle like this, it's also counterclockwise, and this one is the clockwise whole. Okay, so here the number of boundary cycles. Let's first identify the boundary cycles. And let's name each of them. Use the same name. So I have the imaginary boundary cycle. Let's name it cycle infinity, and let's use the same labels for the remaining. So the clockwise, the black one is C1. Okay, this is a whole, and the other is C2. This one is C2. The clockwise here is C3. The counterclockwise C4, cycle 5, and the clockwise cycle 6 and cycle 7. So we have 7 boundary cycles, and we are going to create nodes in our graph for these cycles. So for example, C1, C infinity, C1, C2, C3, C4, C5, C6, C7. Okay, let's have nodes for these. And for the ones that are outer boundaries, we are going to label them by having another circle around them. The imaginary boundary we have such. And for C2, C2 is also an outer boundary of the inner face. And C4 and C5 are also outer boundaries. C4, C5. And C7 is an outer boundary. Okay, so outer boundaries are labeled here, the boundaries that are counterclockwise, And the boundaries that are clockwise, I have only 3 of them. I have C3, C6, and C1. Okay, C3, C6, and C1 are my clockwise boundary cycles. Now, we put, I mean, this is like the notation of having 2 cycles is like these outer boundaries are going to be our final states, final cycles when we are traversing holes to the outer boundaries. So that's why I think they use these 2 circles. Now, we are going to put, from C1, we are going to put an edge to its cycle, boundary cycle, immediately to the left of it. Okay, so C1 is the large one, and immediately to the left of it, there is no cycle actually. So if we cannot find if this half edge C1 does not have other boundaries edge immediately to the left of it, we connect it to the imaginary boundary like this. Okay, if there's a hole and if immediately to the left of it, and as I repeat, this immediately to the left is in the global sense. Okay, I'm not looking at half edges and their local orientation. I'm looking at globally this figure, and I'm looking for, as if on the sweep line, if imagine the sweep, a plane sweep algorithm, on the sweep line, remember the half edges are ordered with respect to how they intersect the sweep line. So the half edge record immediately to the left of C1 is going to be on the sweep line when we are doing the plane sweep algorithm, because they're ordered on the tree. So we can actually find this other boundary cycles half edge during plane sweep. Okay, during plane sweep we can record what is the half edge that is immediately left of this half edge. And for C1, it's an empty set, it doesn't have anything to the left of it. So we connect C1 to the imaginary boundary. And for C6, what we do is, when we go immediately to the left of this C6, okay, this boundary, either this one or this one, both of these half edges, by looking at these half edges, we see that the boundary immediately to the left of it is C3. But we are going to, you may have questions right now, why isn't C4 and C3? How are we going to decide whether it's the half edge? Because the half edge immediately to the left of it seems, as I draw it, the clockwise cycles are on the outside, so it first hits this black one, but how do you know? Maybe it hits these are the same. Don't forget, these occupy the same coordinates, these 2 half edges. So how do we know that we hit C3 but not C4? We are going to come to that. This is a small technical detail that the book does not discuss. But the book says, okay, the boundary cycle immediately to the left of C6 is C3. So we connect C6 to C3 like this. And the boundary cycle immediately to the left of C3 is C2. Okay, so we connect C3 to C2. As you can see, the first edge that I hit when I go from this boundary cycle to the left is this black edge. It's the outer cycle. And the first edge, when I'm going to the left, from this one to this one, the first edge I'm hitting is C2. So this is how I connect them. But how do I know that this C2 is the outer boundary of this hole? Maybe when I go to the left, I may have hit it another hole. So how do you distinguish? The small technical detail here is that when you find the boundary cycle immediately to the left of this boundary cycle, how do you decide that this boundary cycle is an outer boundary or another inner boundary? Okay, so this small technical detail that is missed from the book can be solved by looking like this. The difference, if you look at the difference of C3 and C2, is that here C3, this boundary cycle, does not encapsulating this hole. So it cannot be an outer boundary of this hole. However, C2, if we follow the boundary edges of the C2, okay, we see that this whole C3 is completely inside C2. So when we are finding the boundary cycle immediately to the left of it, by doing some inside-outside test, we can determine whether this C3 is completely inside or not of this boundary cycle immediately to the left of us. If it's not inside, for example, for C6 and C3, C6 is not inside C3, so probably both of them are boundary holes, so we are going to continue going left. Otherwise, if it was an outer boundary, we could, I mean, it could have been something like that. This is what I'm trying to say. There may be another boundary, outer boundary, which we hit when we go to the left. So how do you distinguish between this boundary cycle and C3? How are you going to find out when to stop going to the left? Okay, because here, if you go from here to the left, you may hit C1. So you may ask, why don't we connect C2 against C1? Because C2 was a outer boundary, so we don't connect outer boundaries to other boundaries. So we stop this connection of nodes when we reach an outer boundary. So this is our final graph, okay? So this is what we do. So for each boundary cycle, if it's a hole, we connect this hole to the cycle that appears immediately to the left of it. So that's the rule. But how you do it, the technical details, as I said, is a little blurry because it's how you find when you're connecting this, whether the problem is this, let me tell you again. The boundary cycle immediately to the left of this boundary cycle, is it C3 or C4? How do you distinguish between these two? So that's the main problem.
Hocam bu convention bu şekilde değil mi? Yani aynı line'ı çizerken clockwise dışa çiziliyor.
Yeah, if you do it like, I mean, if you do it in drawing, you are not going to have any problems. But the problem is when you implement it, what does it mean to draw it outside when you're implementing? Because they have the same beginning and ending coordinates. They occupy the same coordinates. So what does it mean to be outside and the inside? Maybe what you can do is, but if you also know actually something else. You know, for which, after you find the boundary cycles, for each half edge, you know whether it's part of a clockwise or a counterclockwise traversal. So if you hit the two edges at the same time, you can choose the clockwise first because it's on the outside. So yeah, you can do it. But then when you're hitting this one, are you going to choose C1? No, because this is going to be closer to that part, so you will be able to choose. If you draw it like this, there's no problem. I mean, in this drawing, everything seems identified. There is nothing wrong. You immediately, as you can see, you hit the red one. The red cycle here is immediately to the left of C3, and the black cycle C3 is immediately to the left of C6. But if you're really going to implement it, you may have some small technical problems to identify between these two different cases. I mean, my solution would be, and in the worst case, what you could do is you can do some inside-outside tests. I mean, whether what you hit completely wraps your cycle. If it's completely wraps, it means that it's an outer boundary. Okay, so this is one way to. So after you have this graph, each separate connected component of this graph corresponds to a unique face. Okay, so this one, it belongs to one. So C6, C3, and C2 are incident to the same face, which is this one. Let's name it F1. This face 1 is the face of these three boundaries. C3 and C6 are holes in this face F1, and C2 is the outer boundary of face F1. And C1 and C infinity are the, so this is going to be F2. So you are going to identify by simple traversal of this graph, you can identify faces as the connected components of this graph. So we are going to have 5 faces. So F3 is this one. F4 is this one. This is F5, and that's it. Okay, so these are going to be our 5 faces of this subdivision, and you can, since you know each boundary cycle, by going through the next edge of these boundary cycles, you can set the face records of each face correctly, and the inner and outer boundary records of each face correctly based on this. Okay, so this concludes our map overlay problem. There's the only thing that we didn't discuss is that for each face we need to also know, for example, this F3, which original faces in this. Imagine this problem we are solving is the overlay of 2 subdivisions. So this is a new face F3 of this new subdivision. This F3, which original faces in the 2 subdivisions that we are overlaying this face 3 includes? Okay, it's going to actually include exactly 2 original faces. This face 3 is going to be connected, it's going to be associated with exactly 2 original faces, because each original subdivision that we are overlaying, the 2 subdivisions that we are overlaying, they are the subdivisions of the whole plane. So there's a face defined everywhere on the plane. So it's like there's a face defined everywhere in one subdivision. There's another other set of faces are defined everywhere in the other subdivision. So when we get when we overlay them, when we have a face like this face should be associated with 2 of the faces of the original subdivisions. And which faces are there are going to be the final thing that we discover. And again, we need to find. Again, we can do it during the plane sweep by using the incident face records of the edges along the sweep line. But this will not be very difficult to set it. For example, if these are the incident, sometimes it may happen that if an half edge, I mean, if this face became due to an intersection of 2 half edges from 2 different subdivisions, we will immediately know what this is going. If at intersection half edges, finding the face associations, original face associations will be easy, but the difficulty arises, for example, when an original face of the first subdivision is included by a larger subdivision, by a larger face of the other subdivision. What we need to do is, for example, if this small face was labeled, for example, FA in one of the subdivisions, and if in the other subdivision there was this big face F1 which was labeled as, for example, FX in the original subdivision. So we need to say that the associated original faces are FA and FX in the subdivisions that you are overlaying. So how are you going to find that in the first subdivision this face was not there? Okay, in the first subdivision this part was also the inside of face X. It became outside after we overlaid these things. So how do we know that this inner part was also, I mean, imagine something like this. This big rectangle may indicate a forest region in one subdivision, okay? The big rectangle is only one face in one subdivision. That big rectangle was one of our subdivisions, and it was indicating a forest. Now, the small ones, for example, were subdivisions that were indicating the height of the trees, okay? For example, it may indicate that there are small trees in these regions and large trees in these regions. But what we need to be able to find is that this is a forest region, and there may be, that's not a very good subdivision, because this subdivisions are already connected by definitions. If I say large or small trees, I assume already there's a forest there. So usually when you're connecting 2 subdivisions, there is no semantic connection between them. So what I'm trying to say is we need to know which original faces the two subdivisions we are overlaying include this region. So that's the last thing that we need to find to compute the overlay of two subdivisions. Okay, so this concludes the line segment intersection and map overlay problems. And if you don't have any questions, I'm going to start with art gallery guarding problem, guarding an art gallery and polygon triangulation. Okay, so let's start with the new chapter, chapter 3. So first of all, let's start with a practical problem, guarding an art gallery. So your goal is, given the floor plan of a building, put cameras at certain locations in this building in which you are going to guarantee to see everywhere within the building. Okay, so how many cameras do you need and where do you place these cameras? So this is the art gallery guarding problem. Okay, given and first of all, how do we represent our building? The floor plan is usually, buildings are usually represented with floor plans. And although the building is three-dimensional, in terms of the third dimension, there is nothing interesting. It's always, we don't have buildings with other walls coming out. Usually the walls directly are horizontal, they're vertical, and they don't have anything extra edges coming out of the extra walls coming out of them. So usually, by just looking at the floor plan, you may be able to identify this, you may be able to solve this guarding problem. So here we are going to represent our buildings or a set of rooms with a simple polygon. Okay? So when I say simple polygon, a simple polygon is defined as a polygon whose edges do not intersect and there are no holes in it. So any convex or concave polygon is a simple polygon. We don't allow edge intersections, and we are not going to have holes in the polygons. And at the end, we are going to see the algorithm we are going to discuss today actually is capable of handling polygons with holes, but just first assume that we are just concentrate on simple polygons. Anything, and when I say simple polygon, actually that polygon can be quite complex, meaning that you can draw a very strange concave polygons many floor plans can be represented by floor plans which are very complex, but still they are simple polygons. For example, something like this. This is the outer. So let's do something like this. I can represent each room like this. Okay, so this is a simple polygon, okay, because it's a concave polygon, but it's a single polygon, okay. So the region inside, so here is inside. So this may be a floor plan of a building. Now, the question is, for example, how many? So first of all, let me describe mathematically what I mean by guarding. A camera placed, for example, if I place a camera here, which part of the polygon this camera will cover, will guard, is determined like this. Any line segment that you drove originating from this camera, you see all the polygon pieces in which if the line segment is completely inside for example, if I draw a line segment like this, it's not completely inside the polygon because this part is outside. So if you are able to draw line segments which are completely inside the polygon, all the points on these line segments are the parts of the polygon that you see. Okay, so in other words, this, if I place a camera here, let me use a different color. If I place a camera here, I will be able to see everything here, and actually I'll be able to see all this red region. Okay? Because this wall here, I will not be able to see any part here, because any point, in order to connect any point here to this camera here, I need to intersect one of the polygon edges. So this line segment that I have drawn is not going to be completely inside the polygon. So if you place a camera here, you're only seeing that part. So for example, what if you place the camera here instead of choosing here? What if this corner here? I mean, it's seeing everywhere inside this small room, and in addition, it's also seeing this large region as well. So it's, as you can see, it's a better choice. Instead of placing the camera here, placing it here gives me a larger area. Now the problem is, what is the number of minimum cameras you need to guard the entire polygon? Okay, so this is the art gallery guarding problem. How many cameras do you need? And in general, you want to find the minimum number of triangles. And let me tell you this, the techniques that we are going to see today is not going to find the minimum number of cameras to guard this polygon, because this problem has proven to be NP hard. Okay, finding the minimum number of cameras to guard a simple polygon is an NP hard problem, and we are looking for efficient algorithms to solve this problem. But at least we are still. Let's continue analyzing this problem. Okay, we cannot find the actual minimum, but can we provide a bound on the maximum number of, can we put a bound on this minimum number? For example, can you say that if this polygon has n vertices, you are never going to need cameras more than n. Okay, so this n is our bound. Our goal will be, can you give me a number saying that, give me a simple polygon, you are not going to need cameras more than that number. And we want to give this number to be dependent on the number of the polygon vertices. If your polygon has n vertices, can you give a bound based on the number of vertices? And an interesting observation is that just the number of vertices does not really tell us anything, because if you have a convex polygon can always be guarded with how many cameras? One camera, yeah. So a convex polygon, that's the definition of convexity, right? Any line you draw between any 2 points should be inside. So definition of convex already has this guarding. You put any camera on any vertex, you'll be able to guard the whole convex polygon. So you may have 20 gone or 100 gone, I mean a very a convex polygon with many vertices, 1000 vertices, you'll still be able to guard it with just one camera. So now maybe what if, can we divide this concave polygon, this simple polygon, into convex patches, convex pieces? And that problem is also very difficult. It's not an easy problem. But we are going to see today how we divide this simple polygon into triangles. This is called Polygon Triangulation, and triangles can also be guarded by just one camera. Maybe dividing it to triangles will help us to identify the number of cameras, and our goal will be to find a bound on the maximum number of cameras that you need for any simple polygon. So maybe a convex polygon can be guarded by one camera. So that's the lowest bound. What is the higher bound? How many cameras you need at most for any simple polygon? Is it n? Is it a tight bound? Can you, for example, guard this with n over 2 cameras? So our goal will be to first find this bound. And we are going to see that any polygon, any simple polygon, can be guarded by at most the floor of n over 3 cameras. Okay, so you need, for example, any pentagon can be guarded with one camera. Okay, it may be it doesn't need to be a convex pentagon. It may be, if you, for example, this 5 over 3 floor is 1, so 1, 2, 3, 4, 5. Okay, so this one we'll be able to guard it with one camera. If you place it here, you'll be able to guard the whole pentagon. Okay, I mean, but if you place it here, it's not going to work. But if you find your camera locations carefully, any simple polygon with 5 vertices can be guarded with one polygon. So we are going to prove this bound. This is the maximum number of cameras you need for any simple polygon. And we are going to also show that this is a very tight bound, because you can always draw a polygon given the number of vertices n. You can draw your polygon such that you always you need this many numbers. I mean, you can have polygons. You can draw polygons in which this number of cameras are really needed. So this is going to be a tight upper bound on the number of cameras that we need. Okay, so first let's start before we prove this. So let's have a break of 10-minute break, and I'm going to